All right, so the last function where I broke it up, I said this interval where the second derivative was equal to 0 or undefined, I said this is where we're going to break up the intervals. And then I mentioned something. It said possible point of inflection, or IP is what I wrote. So what is a point of inflection? A point of inflection is where a function changes concavity. Anytime a graph changes from concave up to concave down, or concave down to concave up, is called a point of inflection. That's written right in this table right here. Again, where concavity changes is a point of inflection. Notice that it is a point on a graph, so anytime we write it, we are going to write it as an ordered pair, x, y, and it's a point where the graph changes inflection. So how do we find points of inflection? It's pretty simple. Just find the second derivative, set it equal to 0 or undefined. Make sure that that point is in the domain of the original function. I can't stress that enough, so let me say it again. Make sure that point where the second derivative is 0 or undefined is in the domain of the original function. If it's not a point in the original function, we can't call it a point of inflection. So always check to make sure it's in the domain. And then you're just going to do a sign chart. And anywhere the second derivative changes from positive to negative or negative to positive, it is a point of inflection. So let's see this in work with the next problem right here. It says find any points of inflection on the graph of negative x cubed. So just a little visual. If you remember what negative x cubed looks like, the graph should look something like this right here. We should see that there's a clear change in inflection in the first part of this graph. It looks like we're concave up because it's the left side of a smiley face. And on the right one, it looks like we're concave down because it's the right half of a frown. So that point right there in the middle should be at the point, it is actually the point 0, 0, should be a point of inflection, but let's see if the calculus actually states that. So again, to find inflection points in concavity, we want to look at the second derivative. The function's negative x cubed. The first derivative of the function would be negative 3x squared using the power rule. The second derivative of the function would be negative 6x. Negative 6x. We know this is never undefined, but it is equal to 0. Divide both sides by negative 6, and we would end up with x equals 0. So this right here, again, is where the second derivative is equal to 0, or the second derivative is undefined. It is not a critical value. This is called a possible inflection point. The only way to determine if it's an inflection point is consider that real number line. Let's plot the number 0 there. We know the second derivative at that point is 0. We need a test point in each interval. I'll use, I don't know, how about negative 10 and 10. Negative 10 is to the left of 0. Sorry, let me write my intervals. Negative infinity to 0 and 0 to infinity are my two intervals. Okay. Remember, I'm plugging this into the second derivative, not the first derivative, so I'm plugging this into negative 6x. When I plug in a negative 10, a negative times a negative is a positive. When I plug in a positive 10, a negative times a positive is a negative. So here, for the first interval, negative infinity to 0, I have that the second derivative is positive, which means concave up. That's exactly what we saw when we looked at the picture. In the second interval, we had a negative number, so that means in the entire interval, the second derivative is negative. Where the second derivative is negative, it means it's concave down, which is exactly what we saw in the graph as well. So there's our concave up, and there's our concave down. So what do we know about this point right here? Because it goes from positive to negative, and again, 0, always check the original function. We can plug in 0 to the original function, so that point would be an inflection point. Remember, we have to write the point as an ordered pair, though, so we know the x value is 0. We need to find the y value of the original function, so we plug it into the original function. We would get a 0, so that tells me the ordered pair, 0.00, is an inflection point. 0, 0 is an inflection point. How did I know it was an inflection point? Again, the second derivative changed from positive to negative at that point. So let's look through the next example on this. Again, we wanted to find any inflection points of this graph. Inflection points in concavity, we always look at the second derivative. So what do? I find the first derivative using the power rule. The derivative of x to the fourth is 4x cubed. The derivative of negative 2x cubed is negative 6x squared, and the derivative of 1 is 0. We don't care about the first derivative, we want the second derivative. So finding the second derivative using the power rule, I'd have 12x squared minus 12x. I set that equal to 0. It's never undefined because that's a polynomial function. I factored out a 12x from both of them, so I had 12x times x minus 1. If I set 12x equal to 0, I get x equals 0. If I set x minus 1 equal to 0, I get x equals 1. Again, this is where the second derivative is equal to 0, so these are not critical numbers. These are called possible inflection points. I drew my number line. I broke it up at those 2 points, 0 and 1. My first interval is negative infinity to 0. In between the two is 0 and 1, and to the right of 1 is 1 to infinity. I need to pick a test point in each one of those intervals, and remember I'm plugging it into the second interval because I care about concavity. When I plugged in negative 1, I got a negative times a negative, which is positive. When I plugged in 1/2 or 0.5, I got a positive times a negative, which is negative. When I plugged in 10 into the function, I got a positive times a positive, which is positive. So the entire first interval must be positive, the entire second interval must be negative, the entire third interval must be positive. So what is an inflection point? Well, first of all, I got to make sure they're in the domain of the original function. Try plugging 0 in, which I did right over here. I got the number 1. Try plugging the number 1 in, which I did over here, and I got the number 0. So it looks like the ordered pairs 0, 1 and 1, 0 are both inflection points because at those points, the second derivative changes from positive to negative at the first one and negative to positive at the second one. Anytime it changes sign, it is an inflection point. Had we had something like positive, positive, that number 0 right here would not have been an inflection point because it did not change sign. But in this case, it did change sign, so both of those are inflection points.